Okay, so here we are with the last two descriptors of motion, okay, of kinematics. And so this question is talking about how fast an object is. So the previous video you would have seen that we talked about how long and how far. Now we're going to look at the last two. This is actually the last of the main questions, and the other ones I call it the bonus fourth question. So here we're talking about how fast an object moves. Okay, again, like how far, it actually has two answers. There's a scalar answer and it has a vector answer. So when we talk about how fast, right, I'm panning, not penning, right? So if we talk about how fast, we're talking about an object's speed. Okay, now it's kind of weird that it's going to have a V, a symbol of V, it's not S. The speed, when in math class, when you did those DRT problems, that is the same thing as speed, that rate. Okay, so distance equals rate times time is simply just the rate of speed. Okay, so it is a scalar quantity, and it's just going to refer to how fast an object is moving. Okay, and so what happens is fast-moving objects cover a large distance in a short amount of time. If we have another object that is now moving slower, it's going to cover the same amount of distance but longer period of time. So if I want to go fast, I'm going to cover a large distance in a short period of time. If I want to go slow, I'm going to do that same distance, but do it in a longer period of time. So the SI unit for speed is meters per second, right? Or we'd say M over S. Again, this is the SI unit, so this is what we need to use. If you have anything else besides meters per second, you need to convert. The big conversion, miles per hour to meters per second. Okay, kilometers per hour to meters per second is easy because it's like just basically going between prefixes. With the miles, and I gave you the conversion factors in the last video, about 1 mile is 1,609 meters, and that 3,600 seconds is 1 hour. So an object with no movement, if it hasn't moved, it has a speed of 0 meters per second. We say that it is at rest. Okay. At rest, comes to a stop, they all mean the same thing, that's 0 meters per second. Okay, so just some speeds. If we're looking at here in terms of physics, 5 meters per second. If you're in your car, 70 miles per hour. Okay, one thing to note is I didn't put a direction on it because it's a speed. And then you could, you can have something like 2 inches per year, right? And that could be more like a study in like earth science or geology, where you talk about like glacial movement or erosion, right? That glaciers move 2 inches per year, right? That's on average it's been moving, okay? So speed is simply distance over time, or I should say total distance over the total time, okay? And that's more in terms of the words, or you can just say it's x over t. Right? So there's yet another physics formula for you. Your first one would have been the displacement formula in the last video. And so now there's your kind of first, more of a descriptor type equation. So you're just going to find the total distance traveled divided by time. And if you want to think about it in terms of stuff you're used to, the distance will be like what you get from Google Maps, right? So it tells you to go 5 miles one way, turn 2 miles the other way, and at the end it says it's going to take you this long, or this many miles and this many hours. That's actually giving you the average speed, okay? Now, the vector answer is very simply velocity. And these are two words that people want to interchange, but once you go into the physics classroom, it's different than once you go out of the physics classroom, okay? And so we got to put this little symbol. So it does have the same variable of v, but we got to put this little like half arrow. That's actually the vector symbol, okay? You'll see it pop up with acceleration as well, but sometimes textbooks will just boldface it, and sometimes they don't write it, and it's what comes after tells you if it's vector or if it's velocity or speed. You'll see here in a second what we mean by that, and that's associated with the formula. Right, so it is a vector quantity, right? It describes the rate at which an object's position changes. It's direction aware, which means you have to include those directions, the plus, minus, the angle, you draw an arrow, you got the north, south, east, west. But because it does answer the question of how fast, it is also measured in meters per second. right? It doesn't matter that it's a vector or a scalar. The unit's always going to be the same. So length over time. Okay. Some examples, right? So if I go and back to some of those examples from before, right? Positive 5 meters per second, 70 miles per hour west. So now you can see I'm specifically telling you which direction I'm heading. And if we do our glacial, let's say, it looks like the glacier's turning. And so the scientist is studying it's 2 inches per year at an angle of 10 degrees. Okay, so you can see how I've now incorporated that direction in there. Okay, and the formula is simply the change in position over the change in time. Okay, or displacement over time, or x minus x0 over delta t. And I do want to point out this term rate is changing in a quantity over time. Okay, and that's a math term, all right? If you take calculus, you'll see that pop up again because it'll talk about a derivative is the rate at which something changes. Okay. Now, a car, you can find this information on a car pretty easily. There's 2 things that you can use. So the speedometer of a car, right? Now, that's not going to give you what we consider to be average speed or average velocity, which is what the previous 2 kind of terms were, but it's going to give you an instantaneous speed, okay? And if you want to bring in the velocity part, you would have to look at there is a direction. Most cars now have compasses on them. But you can see that word instant, right? That just means at a particular moment in time. So if I look at my picture here, right? If I look at this, I want to say how fast I'm going. My dial is there. I'm going 60 miles per hour, right? I'm looking down at that moment, and that's what it's telling. Now that speedometer is more for America, right, or the United States, because it is in miles per hour. You'll see that now most cars have a kilometer per hour as well. My car is a Volvo, and I have the kilometer per hour on there because it's made in Sweden. Okay. Now to determine the average speed, right? Your car has an onboard computer, and you can see it kind of hiding behind this little circle here. You'll see the first thing here is your miles per gallon, so that's how many miles you travel for your gallons used. But it's these next 2 lines in it, really the next 3, sorry. It's the next 3 that kind of give you an idea of your average speed. So the average miles per hour would be your average speed. And then it's because your computer is going to take the distance and divide it by that time. So if you did 979, that's in miles, right? So 979 miles divided by 36 hours and 24 minutes. You would have to convert that 24 minutes to kind of a decimal form just by doing 24 over 60. You'll find that your average miles per hour is 26 miles per hour. Now keep in mind, if you look at these 2 values, your 60 miles per hour, your instantaneous speed will always be larger than your average speed. Because remember, the average speed or average MPH there takes in consideration all those little times your car stopped. Every time you're going 10 miles per hour versus 70 miles per hour. And roughly, it'd be amazing. It's always in that 20 to 30 range somewhere, just because that's how it works out. Okay. And you can do that calculation real quick. Just select that on your onboard computer, and then you can do the quick calculation. All right. All right. So here are just some more examples, or some examples pertaining to this. And this is kind of like we go back to our number line example. So remember when we did the distance displacement, we started at positive 1. We end up at -1 or -6. So it had a length of 7 meters, right? So our distance traveled was 7 meters, and our displacement was -7 meters, right? And this is from the previous video. But now we're going to do the speed and velocity. So we're going to do speed is x over t. So really all we're going to do is take that 7 meters and divide it by that 4 seconds, and we're going to get 1.75 meters per second. Okay. Again, notice I didn't put a direction there because speed is a scalar quantity. Now we're going to come over here and do our velocity. So it's change in x over the change in t, or change in x is displacement. So we're going to do -7 meters over that same 4 seconds. And you're going to see that really the difference is the fact that we got a negative sign now in front, right? Because we travel to the left, which means we're going in the negative direction, which means that our velocity would be negative. But what you will see is the magnitude is the same. If you continue in a straight line, the magnitude of the speed and velocity, right, of those 2 values are going to be the same numbers. Okay, but what's going to be different is, one will have a sign, one won't have a sign. And kind of a simple way to think about speed in straight line situations like that, if you don't have to do any twists and turns, that speed is just the absolute value of the velocity. Okay, that doesn't hold true like in this example. In the next example, when we kind of we went back and forth, and then so we started at 1, went up to 8, and came back to -9. That idea that speed is the absolute value of velocity doesn't hold true here, because you remember our distance was 24 meters, but our displacement, was -10 meters. So note that these are not the same numbers, right? These are not the same physical magnitude. So again, if we do our x over t, we're going to get 24 meters over 15 seconds. And I apologize, I need my calculator. That I can't do in my head. I just dropped it. All right, so we're going to do 24 divided by 15. So we're going to get a speed of 1.6 meters per second. And then we go over to our displacement or velocity. We're going to get change in x over the change in t. So we get -10 meters over 15 seconds. And we get -2/3. But one thing to remember is that in physics, we want decimals. Okay, because decimals mean approximate, and we're always rounding numbers, where a fraction is an exact value. That's something you use in math class. Okay, now those two examples kind of tie back to the examples we've already done. Okay, and then let me just shrink that. No, let me just kind of shrink a little bit so we can see the entire question. All right, so these next practice problems all involve the speed or velocity calculation. Okay, and you'll see that they all talk about speed. All right, so the first one is, how long would it take you in hours to drive from Miami, Florida to Seattle, Washington? So if you literally go from the tip of one part of the country to the tip of the other part of the other side, it tells you it's about 3,300 miles or 5,300 kilometers. Now, if you can average that in 60 miles per hour or 96 kilometers per hour, so we're going to, I'm panning, not penning, it's pen, right? And I'm going to write both of the calculations up here because, I mean, ultimately it does say in hours, and the units for both of our speeds are given in hours, okay? But we want time, right? So we got to do a little algebra here. So the first step we're going to do is we're going to multiply both sides by t. To bring it up, that's going to cancel. I'm going to get x equals dt. So note that if you're solving for your distance, and then we're going to do our last step, which is we're going to divide both sides by v because we want t by itself. So let's cancel those v's. So t equals x over v. All right, and now we can plug in our numbers. So 3,300 miles. If you get something like this, make sure you're plugging in the right units. Right, we're using the right values. MPH is miles per hour, okay? So you get 3,300 miles per hour, and we're going to divide that by 60 miles, or 3,300 miles divided by 60 per hour. And then we're going to do 5,300 kilometers and divide that by 96 kilometers per hour. And you're going to find you're going to get approximately 55 hours, right? If you want to talk about how many, that's about three plus days. Right, just over 3 days and 7 hours. Okay, it will take you that long to get from Miami to Seattle, Washington. Okay. All right. So the next one, you got sound traveling through the air at 344 meters per second. If you hear the thunder about 5 seconds after seeing the lightning bolt, how far from you in miles, which is 1,609 meters, did the bolt strike? Okay. This isn't one of those fun little things. As you're a kid, your parents may tell you, your parents or guardians may tell you. Oh, all you have to do is count the number of seconds between you see the flash, and then when you hear the thunder, it gives you an idea of really how many kilometers, I think, is what that kind of rough estimate does. So we're going to solve this. So we're looking for x, right? Penning, not penning. That's pen. Okay, so I've already done the algebra. It's right here. It's this, right? X equals vt. So I'm going to do 344 meters per second And the reason why that happens is because light travels so much faster than sound, right? Light is 300 million meters per second, and this is only 344. Okay, and then so we're going to multiply that by 5 seconds. Again, I apologize, I can't do that number in my head. So 344 times 5 gives you 1,720 meters, but we want it in miles, so we have to do a quick conversion factor. Right, gives us practice from that unit 0 stuff. So 1,609 meters is 1 mile. So if you look at it, it's going to be just over, if I estimate, it's going to be just over 1 mile. So it's about 1.07 miles. Okay, so that's pretty close. Right, that's 5,000, just over 5,280 feet, probably about 5,500 feet. So that's not too far away. When I was growing up, I remember there was a lightning bolt that struck in the street, like literally right outside my house. It scared me. Okay, so if I did it, I would have been under like a second. I would have been like a quarter of a second or less. Okay. All right, the next two problems are great because they talk about going in circles. Okay, so this one says it takes you 50 seconds to go around the circle of radius 50 meters while running at a constant speed. Find that constant speed. So what happens is the distance that you traveled is not this number, but because that's the radius, it tells you, right? So what you're going to travel is actually, all right, the circumference of that circle. And you have to remember, like all that stuff, circumference and area is going to come into play here. So you got 2 pi times 50, 628 meters. Okay, so that's 1 lap is 628 meters. So if I want to find that speed, we just use x over 2. All right, so we're going to do 628 meters over, hold on, sorry, that's not 628 meters. All right, it's 314 meters. I was jumping the gun, right? The answer is going to be roughly that 300 or 628 number, or 628. So we're going to do 314 over 50, which actually works out to be 6.28 meters per second. Okay, so that's how fast you'd be traveling around this circle. Okay, the next practice problem says you go around a circle of radius 30 meters with the speed of 5 meters per second. How many laps do you do in 2 seconds? Okay, so the first thing we need to figure out is how long does it take us to do 1 lap? And we've already done the algebra for this. It's x over v. Sorry, that's kind of a weird x. I'm starting to write v. My mind was jumping ahead of my pen. So we're going to do x over v. And so we're going to do 2 pi times 30, because that's how far we're going to travel. We're going to divide that by 5. Okay. So 2 pi times 30 divided by 5. So it's going to tell us that that's 37.7 seconds per lap. Right? But we want to know how many laps per second, so we're going to do 120 seconds. And again, we're going to make this look like a conversion factor. So it's going to be 37.7 seconds for 1 lap. So if I do my canceling, what's the only thing left is laps, right? I mean, laps to us is technically a conversion, right? So it's going to tell us it's going to be right about 3.18 laps we're going to do in 2 minutes. Okay. Now, quickly, I know this video is getting kind of long, but just real quick, it shouldn't take us too long. Actually, I'll stop the video here because